Okay, well, so far we've been talking about regression trees. The response was quantitative, salaries in this case of baseball players. Oftentimes trees are used when the response is a categorical variable, and so then we call those classification trees. But you'll see the technology is very similar, and we just have to change essentially the loss function and how we measure good performance. So let's see how that goes. So we're going to predict in a classification tree each observation belonging to the most commonly occurring class. So that's what's going to happen in the terminal node of the tree. Instead of just giving the prediction being the mean, we're going to classify it to the most common class. We're going to grow the tree in a very same way as we did for regression trees, but we don't use residual sum of squares as a criterion for making the splits. We need a criterion that's more geared towards classification. So one thing you can do is at each internal node, you can just look at the classification error rate. And that's easy to compute. So suppose class K, I beg your pardon. So suppose you've got capital K classes, and you compute the proportion in the terminal node in each of the classes from 1 up to capital K. Well, the class you're going to classify is the class that's got the largest of those probabilities, those proportions, and the error you're going to make is going to be 1 minus that maximum, right? So all the ones that don't belong to the maximal class are going to be counted as errors. So you could use that to decide on the split, and so that's the proportion of errors you're going to make. But it turns out that that's a little bit jumpy and noisy, and it's not very. It doesn't lead to a very a smooth tree growing process, and for that reason, some other measures are preferable. One measure is the GNI index, and it's a kind of variance measure across the classes. So you've got K classes, capital K classes. Often K is 2, but not necessarily. And this, for those who know the binomial distribution, this is each of the terms here is like a binomial variance. And in fact, for the multinomial, this is the diagonal of these are on the diagonal of the covariance matrix. So this is a measure of total variability in that region. And if the GNI index is really small, what that means is pretty much one class is favored and all the rest are really small.
Right, as an extreme case, Trevor, right? If the region is pure, so it's all one class, then one of those p hats will be 1, the rest will be 0, and G will be 0.
That's a good point. And on the other hand, if they're all equally distributed in the classes, this GNI index will be maximum. But it moves it changes in a smooth way. So that's one of the criteria that are very popular. And it's also known as a purity index. It measures the purity of the class. An alternative is the deviance or cross entropy, and this is based on the binomial log likelihood or the multinomial log likelihood. And it's a measure that behaves rather similarly to the GNI index. And either of these are used and give very similar results. So let's look at an example. We'll look at the heart data. These data have a binary response called HD. There's 303 patients, and they're all represented with chest pains. So the outcome has a value yes, indicates the presence of heart disease based on an angiographic test, while no means no heart disease. For these data, there are 13 predictors, amongst them age, sex, cholesterol, and other heart and lung function measurements. And so we ran the tree growing process with cross-validation, and we'll see what we get in the next figure. At the top, you see the full tree grown to all the data, and you can see it's quite a bushy tree with an early split on thal.
It's a thallium stress test.
A thallium stress test, okay. And then the left and right nodes were split on Ca.
Calcium, I think.
Which is calcium. And then the subsequent splits, it's hard to see here, but these pictures are in the book. So quite a bushy tree. And you see at the terminal nodes of this tree are the classifications no or yes. So that means an observation that, for example, ended up in this leftmost terminal node here, the majority in that class were no's, no heart disease, and so the classification produced would be a no. Whereas the right-hand one here is a yes. Interesting, this terminal node has two no's. So if they both predicted no, why was there a split here at all? Well, it must mean that one of these nodes is purer than the other. So even though they were both ended up having a majority of no's, the one node was purer than the other node. And the GNI index would identify such a node. So this tree is probably too bushy. And so once again, cross-validation was used. And again, we see in the right-hand panel the results of cross-validation. And we see the training error, the test error, and the validation error. Here we've actually looked at the training error averaged over each of the cross-validation folds, which is why it's a little jumpy, and actually even increases in one point here, because the trees and the architecture of the trees are different in each of the folds. The cross-validation and test error, we had a left-out test set here as well. Those curves look pretty much the same, and we end up seeing that a tree size of around about 6 tends to do well. These bars on these cross-validation and test curves are standard error bars, so there's quite a bit of variability here. The data set's not that big. And on the right here, we see the pruned back tree that's pruned back to size 6. Of course, the pruning was again governed by the cost complexity parameter alpha. And this here will be a subtree of the big tree grown, and that gave the best classification performance, which is estimated to be around about 25% error in this case. In this figure, we show we compare trees with linear models. Trees aren't always the right thing to do, and so to contrast that, we look at two different scenarios. In these cartoons here, the truth is indicated by these two colors. In this top left panel, the truth is actually best depicted by a linear model. So the decision boundary, in this case, between the two classes is best given by a line, okay? And in this case, a tree is not going to do very well. We see a tree's attempt to partition this space. And, you know, while it does a valiant job, it just doesn't do well enough, because it's confined to big boxy regions, right? So there'd be a split over here, a split over there, and then this region was subdivided, then that region was subdivided, in an attempt to get at this linear decision boundary. So this would be classified as beige. This would be classified as green, beige, green, and so on in a steppy fashion. On the other hand, in the lower two panels, the optimal region is a blocky kind of partition region. And here a linear model is not going to do well. In the left panel, we see the best linear approximation to this decision boundary, and it's going to make lots of errors because, you know, with one single linear boundary, it's hard to approximate a rectangular region like this. And of course, in this one, a tree will nail it. So with two splits, it can get the decision boundary perfectly. So some problems are more naturally suited to trees, some problems aren't. And so the idea is we're going to think of trees as one tool in our toolbox, and we'll use it where appropriate. But of course, we'll also bear in mind simpler linear models as well.
So just to wrap up the section on trees then, we've seen there's advantages and disadvantages. In a sense, they're simple if the trees are small, not too many terminal nodes, because they're easy to display and to understand for non-specialists. And for example, we look back at this heart disease tree, right? The pruned one in the bottom right. A doctor might like this tree because it mimics, in a sense, the way his decision-making process might work. In other words, trying to decide whether a patient has heart disease, he might first do an initial test based on thallium stress test. And if they fail that test, then do a further test based on calcium and decide about heart disease. If the test was passed, we might, again, do a calcium test and then followed by some other criteria. So you stratify the population in a series of simple rules to try to determine whether a patient is of high or low risk. So for that reason, trees are popular because of their simplicity in the fact that they mimic the way some people make decisions as a series of splits. And they can be displayed in a simple tree, which means, again, they're attractive because there aren't equations to have to understand. They can also handle qualitative predictors without the need to create dummy variables. In other words, some of the categorical variables can have more than 2 levels, and you can split a categorical variable into 2 sets of subcategories. So these are all good things. The big downside is that they don't predict so well compared to more state-of-the-art methods. And we'll see, for example, for the heart data, that the prediction accuracy of a tree is not very good compared to other methods. The other methods we'll talk about now actually use trees, but in an ensemble. They combine trees. They build many trees on the same data, and then they average or combine them in some way, and in the process, they improve the prediction error substantially.